In this video, we'll talk about how do you describe alternating current and how do resistors behave in alternating current. And these are really two separate subjects, but we're going to have a narrative that sort of switches between them and overlaps them. And the reason why is that some of the ways in which we describe alternating current are better motivated by discussing how resistors um, behave in alternating current. So I'll use the resistor discussion as a motivation for why we describe alternating current in certain somewhat bizarre variables. If you haven't run into them, though, seems strange. Let's talk about the two most natural ways of talking about alternating current. Well, we want to talk about what is the voltage and current at this very second. That's the instantaneous values for the current and the voltage, because both of these will be changing over time. Now, we've previously just referred to these by the capital letters I and capital delta V. Now, we're going to now have the exact same meaning, but now write them as lowercase letters. So a lowercase I and a lowercase delta V to change our notation to clarify that we're talking about instantaneous values. So what's it like at this moment? It may be high at the moment, it may be low at the moment, it may be zero at the moment. Part of the reason we do this is that we'll reserve these uppercase letters to mean describe what goes on over long periods of time. And here's what I mean by that. One of the ways we describe this changing voltage difference or this changing current is to talk about how high the peaks are, or it's sometimes called what's the maximum voltage and the maximum current in here. Because it repetitively keeps going up to that same maximum value, it tells you about what this curve looks like over time. And we'll use this, for example, as the max current and the max voltage drop. We will have other variables that describe essentially how large this wave is. So this directly is essentially the amplitude of the wave, but we'll give another variable soon that isn't the amplitude of the wave, but it refers to, you could infer the amplitude from this other variable. These different variables are going to have some subscript here. So for example, the maximum current is I sub max. The thing we're going to talk about is an RMS value, and it's going to be I sub RMS, for example. And both of these describe the amplitude of the wave, whereas, and we'll use capital letters for that. We'll use lowercase letters to mean exactly at this second, where are we on this curve. Now, the equations that go with it, by the way, are that the current is the maximum current times a sinusoidal function. Here in this case, just sine. It's 2 pi f times the time. If you remember harmonic motion, this is the same equation here. F is the frequency. Frequency is just how many times per second does it hit a peak. So if, for example, if it was twice per second, that it was the peaks came twice per second, the frequency would be 2 hertz. Hertz being 1 over a second. If 3 times per second it reached a peak, it would be 3 hertz, and so on. Now, we're going to talk a lot about energy in these circuits, so I just wanted to give you a brief overview about how energy is being stored and lost and so on in this case. The power supply will add energy to the current in the circuit. Resistors is where it'll lose it, and capacitors are just where it stores it, and inductors also store it. So the only thing that actually loses power is in a resistor. Okay, so it goes in through the power supply, gets lost out of resistors, and it just is temporarily stored in capacitors and inductors. Now here it's going to be constantly changing, because the amount of energy that's being stored in a capacitor and the amount of energy being stored in an inductor, which makes it more difficult to describe. But here's the broad picture: is this is how the energy is essentially flowing through these types of circuits. So let's talk about how energy is lost, because it only is lost through resistors. We're going to use the equations related to resistance. Now we can ask a couple questions. We can say, at this very moment, how many joules of energy are being lost every second? So what's the power in that case? But that's not particularly useful because at the moment it may have zero power, but on average it may have a significantly higher power. And if we're talking about, for example, the power that goes for a light bulb, because we're plugging a light bulb directly into an AC power supply, so the amount of energy that's being lost is actually varying over time. So the thing that actually gives you the brightness of the light bulb is not the instantaneous power, but instead the average power. So if we look at it over some interval of time, some rather long interval of time, and we talk about how many joules did I lose overall in that time, divide that by the amount of time, that is the average power. How do you get this from our formula off of these different values? The instantaneous use the instantaneous current. This was just the P equals I squared R formula we had from before. Exactly the same, we just changed our notation slightly to write a lowercase I just to try to avoid confusion with the other variables. But this is a different quantity. The average power is not the same thing as the instantaneous. So what goes on the right hand side? And the answer is a current. It has to be the same current in this formula. It has the same units and so on. But this is a specific type of current called the RMS current. It's similar to the maximum current, but it isn't the maximum current. You don't want to plug in the max current to find the average power. The reason why is that if you plug in the max current, you'll find the maximum power. But the power ranges between the maximum and zero over time. So if you want an average of it, it's going to be less than the maximum and it's going to be greater than zero. It's somewhere in between, and exactly where it is related to this RMS current. So what is an RMS current? And what are RMS quantities in general? Because we're going to talk about RMS voltages and RMS currents. What does this RMS stand for? Well, RMS literally just means root mean square. Think of it as a type of average. So it's not the usual average where you just take several values and then you just add them all up and divide by the number of values, and that's the mean. Here what you do is you first square all the values. So in the case of, say, the current, what I would do is I look at every pixel in this line. So I'd have a list of a ton of different values for the different currents along here. Then what I would do is I would square each of those currents, that is numbers, making them all positive. So if the current was positive or negative, when you square it, you get a positive number. Then I'll take the average of all of those squared values. Then I take a square root of that final average, and that is the RMS quantity. So when I say RMS, I write the root mean square is the order of operations that I would write it down. So if I first wrote down a square root, inside of there I would do an average, and then inside of that I would do a squared. It's the opposite in order in which it is actually being performed. So the first thing you do is you square the values. Then you take the mean of the values. Then you take the square root of the values. So the phrasing is a little confusing. It's the way in which you write it rather than the operations, the way in which the operations are being performed on the quantities. First you square it, then you mean it, then you root it. But that is just the traditional way of writing it. Now, if you have a sine wave, there's a fixed relationship between the maximum of that value, like current or voltage drop, and the RMS. And the answer is that you just divide the max by square root 2, which gives you something like 70% of the original value. So if, for example, the maximum voltage was 100 volts, then the RMS voltage would be around 70 volts. As FYI, when we say that the voltage on the wall outlet is 120 volts, we actually are telling you the RMS value. The maximum value is larger than 120 volts. So the reason why is because that's the voltage that you would use in order to find the power, because that would be the voltage you would use in order to find the current, which then you can find the RMS current, you can find the power. So there's a simple relationship between these two quantities. They're proportional to each other, and it's just divided by root 2, but you have to know which value you're going to plug in. Are you going to plug in the RMS, or are you going to plug in the maximum? So I'm going to talk about how do you find each of these different types of quantities. So for instantaneous, all of our formulas we've had before just works and exactly the same as they did before. For example, the power is I squared R. It is also equal to delta V squared over R, which is equal to IR. But the only thing is that you use the lowercase letters instead of the uppercase to make sure that we are clear that you're talking about the instantaneous values. Same thing for the voltage drop across a resistor. Is still given by the same formula. Only thing is we change the notation, so this is now lowercase v and a lowercase I. Average quantities, the only thing that we actually are going to talk about is the average power. If we want to find the average power, you plug in the RMS quantities. Okay, so I RMS squared, delta V RMS squared over R, I RMS times delta V RMS. So we can use all of our power formulas to get the average. We get to the average power, but we use RMS quantities in that case. Okay, and that's essentially why we talk about RMS in the first place, is that that's the things we have to plug in to get the power. It is still true that the Ohm's law works if you plug in the average values. The boring thing is that the average of the voltage drop and the current are just 0. Because if we look back at these curves, for anything that's sinusoidal, there's as much up as down. There are as many positive values as there are negative values, so the average value is simply 0. Which is why we only talk about the average power. Average voltage, average current are just boringly 0. No need to find them in any problem. The other way to talk about it is a peak value, and you can use the formulas as before with the max or peak, depending on how you want to call it, subscript. So you can, the peak power is the peak current squared times the resistance, or the peak voltage drop squared over the resistance, or the product of the peak current times the peak voltage drop. And again, you can either call it peak or max equivalent. Ohm's law still works if you plug in the current and voltage drop maximums. So everything is correct here if we just use the peak ones. If I want to talk about RMS quantities, Ohm's law holds, but the power does not. Meaning that the RMS power is not if you plug in the formula, if you plug in the RMS currents and so on. That's, remember, for the average. Average, not RMS. You could talk about the RMS current. You could talk about the RMS power, but nobody does. It's not really used for anything. If you did, you'd have to plug in a different current in this spot for whatever type of current goes into this formula. It's not an RMS. It's not peak. It's not average. It's not instantaneous. It would have to be a new one. So we won't go into it because we don't have a formula for it, and nobody uses it. So the only thing we use for RMS quantities are voltage drops and currents, and they still can be related with Ohm's law, and that's what I want to note. So we'll have 4 different ways of talking about basically every quantity. Power, voltage drop, current. So any of these things that can vary over time now have 4 different ways. So automatically, alternating current has gotten significantly more complicated because we have essentially quadrupled the number of equations. And sometimes we can use our old equations and sometimes we can't. So it's just remember when this is. And essentially power is really the only one that is problematic, and the only thing you have to worry about is that the average power uses RMS, and you don't ever want to talk about the RMS power.